Hello, how we doing, guys? It's chemistry time, after all. Yeah, it's sorry, I'm just doing things and thinking at the same time. It's really weird. Who have we got? We got Louis, Hadia, Faye, Missy, Megan, Christine, Shidley. Oh, look at this! Got our regulars in the house. That's awesome. Glad to have you back. Glad to have you back as usual. Hey, Ruha, Benyon, Kerry. Excellent, excellent. So, how are we feeling, guys? Just, in terms of, completing your year 12 study. So, obviously, speaking to the year 12 students here. So, um, how are you actually dealing with this? I mean, what is it you're doing day to day? Do you have a routine? Are you literally doing nothing other than just coming to watch us on YouTube? Like, what are you actually doing right now? I'm really, really interested as to kind of get an idea of what you guys are doing day to day right now, because of course we're obviously still doing stuff behind the scenes with TT, planning what we're going to be doing with you guys over the next few weeks and stuff. But yeah, I want to know what you're doing other than these lives, because obviously I kind of see you guys for an hour a day or a couple of hours a day, and I want to know what else you've been up to. So, Louis, feeling hopeful. The live streams are giving me my day a good structure. That's great. That's good. Um, Working more than you do in school, Megan. Fantastic. Just aiming for 5 action hours a day. That's great. That's great advice, Hadia. Yeah, just doing 5 hours a day is great. Even if it's 3 hours a day, then you're doing something, aren't you? This is really, really important. Um, T-Boy's bored in quarantine, yeah, aren't we all a little bit? But then again, to be fair, working from home for me, it's kind of like nothing's really changed other than I don't go out as much. Benyon relying on TT. The mic feels a bit dodgy. Is it weird sound for anybody else? Um, Netflix. Just in a word, T-Boy, Netflix. Yeah, fair enough. I mean, I've been catching up, I must admit, on a bit more kind of Netflix series and stuff than I need to. Um, Doing work set on Google Classroom. Yeah, that's good. That if teachers use Google Classroom and stuff, that's pretty good. Um, So just going to start these classes, so going to be motivated to do other work. Yeah, but again, that's why we're here, hopefully to kind of motivate you guys and keep you guys in touch with your studies. It's really, really important. Okay. What have we heard about on the news? Soon enough, it said in the news. What are we talking about here? Give me a clue. There's got to be a blackout. Oh, there's going to be a blackout. No, there isn't. Okay. No, I think there's been some talk in the news about electricity supplies and people being at home and increased demand and stuff like that. But think about it, okay? I would say a high percentage, I'd say more than half of the electricity produced in the UK is used by industry. Right now, a lot of those industries are shut down. So in fact, the whole population in the UK could be using electricity at the same time, and it wouldn't be using as much as it would if industry was going right now. So no, there's no reason for a blackout. Okay, no habits and stuff like that around the UK and around the world, in fact, which is really, really interesting. But there we go. We're getting off topic now. So let's talk. Let's talk kinetics. Let's talk rates of reaction, ladies and gentlemen. Okay, so I'm going to share my screen and we're going to do what we were here to do, and that is basically have a bit of a best of, look at kinetics and rates of reaction, etc., etc. Okay, so hopefully you're all seeing my blank iPad screen now. I mean, oops. This is basically kind of labeled differently in different specifications, but kinetics nonetheless. Okay, so it's rates of reaction stroke kinetics that we're doing here. So what do we need to know? Well, we need to know our particle theory, okay, or collision theory. That's really, really important. Now, I think there's not much to that extra from GCSE. If I'm honest, maybe, a slight change in tact in terms of like the key terms and stuff that we use. That's absolutely fine. What can help us though are our Maxwell-Boltzmann distribution curves. So we'll spend a bit of time talking about those today. Then, of course, there are the practicals. Okay, so the practicals involved, okay, they're slightly different for different examples, but there's some generic ones that we all do need to know about. Energetics is different, Dennis. Energetics is what we did yesterday, where we were talking about enthalpy and stuff like that. So kinetics is rates of reaction. All right. So other than that, there's not a massive amount we need to do. You do a lot more on kinetics in year 2. This is all like very qualitative, you know, increase rate of reaction, decreases rate of reaction. In year 2, we start looking at the rate equation and quantifying the increase in rate and or the decrease in rate or whatever. Okay. So there's really not a massive amount in year 1 that we really need to do. But you know what? We're going to go over it. We're going to get through it. Okay. So first of all, let's talk collision theory, okay? Now, of course, in order to react, 2 molecules must actually collide, okay? So 2 molecules must actually collide like so. Now, not only do they need to collide, but what else must be true if a reaction is actually going to happen? Orientation, yep, so correct orientation. It's not massively important, that, but it's true. Okay, so correct orientation could be important. Good. They need enough energy. They need to react with sufficient energy. Okay, so not only do they need to collide, probably with the correct orientation, but definitely with sufficient energy as well. Okay, because normally, you know, a lot of the molecules that do collide, they don't react because they don't have enough energy. So they need to have that sufficient energy, aka activation energy. I'm just going to put that as EACT. Okay, so you need that sufficient energy. So whenever it comes to your explanations in terms of collision theory, you need to mention that. Okay, it's about collisions, the frequency of collisions, and the energy in which that they have in order to react. Okay, so let's think what types of things actually influence our collision theory, influence the rate of reaction. Okay. Screen's a little blurry. Yeah, I think, yeah, it's just sometimes it does go like that. Mine's a little blurry right now as well. If you kind of click back a little bit on the, click around on the timeline bar, and it should kind of right itself for you. Okay. So, all right, so we're all on this. Temperature, energy of reactants, pressure, lowering the activation energy, concentration. Awesome. Right. So I'll tell you what, let's start with concentration. So if we increase the concentration, what happens? Well, we have a greater number of molecules. Well, I'm going to say particles. I'm using particles because we don't want to say atoms or molecules. We just generally what we're dealing with. Greater number of particles per unit volume. Okay, so we have a greater number of particles per unit volume. So why does that increase rate of reaction? Okay, good. Okay, Jacka, molecules are more likely to collide. Reactant molecules, I don't think you need to say that. I think just particles is fine because we're assuming that this is a one-way street in terms of a reaction. So a great number of particles per unit volume. Therefore, okay, we have an increased frequency. Okay, using the F word, really big and clever here. Okay, so increased frequency of collisions. Therefore, increased frequency of successful collisions. Okay, because it's all about probability, isn't it? Okay, if you're getting 100 collisions per second, but then you increase the concentration and you get 500 collisions per second, so frequency of collisions, then, you know, if 1% of them are successful of that 100, well, that's 1. If 1% of the 500 are successful, well, that's 5%, isn't it? So a greater number of particles per unit volume increases frequency of Jacka, thank you very much. I'm pleased I nailed that. So increased frequency of collisions, therefore increased frequency of successful collisions. Okay, it's really, really important that. So that explanation there doesn't Molecules have greater energy. Sorry, molecules of energy greater than activation energy. We don't really need to talk about that here, okay? Because, you know, it's part and parcel of the larger explanation. You know, they need to collide with sufficient energy. But what we're saying is here, if we increase the concentration, we're not changing the energy of the particles. We're not changing the distribution of the particles, are we? And we're going to get onto Maxwell-Boltzmann in a second. All we're doing is increasing the frequency of collisions, all right? Like I said, if there's 100 collisions and 1% are successful, well, that's one successful collision per second. If you increase the concentration and there's 500 collisions per second, then it's still at 1%, then you're going to get 5 collisions that are successful out of those 500, okay? So it's about proportion, it's about probability, isn't it, at the end of the day, okay? So what I will say is that there is another, and you mentioned it just a minute ago, somebody did anyway, there's another changing condition that basically this gives the same explanation. So what other changing condition would actually work for this as well? Rasab saying surface area, T-boy surface area, Jacker pressure, big team pressure. Yeah, to be fair, both of them, okay? So, and pressure. So all we're doing if we increase pressure is, it's like decreasing the volume, okay? So it's kind of like condensing things down. And again, you have a greater number of particles per unit volume, all right? So by increasing the pressure, you know, low pressure is kind of like this, high pressure, if you decrease the volume, is going to be like this. So you're kind of increasing the concentration by increasing pressure, aren't you? So the explanation is exactly the same, okay? So I would say for surface area, it is slightly different the way in which you would explain it. So yeah, we'll cross that bridge. It's very, very similar, but it's not the same. But as far as I'm concerned, if somebody asked you, why does increased concentration increase rate of reaction? There's my answer. But it would be exactly the same answer as if somebody said, well, what happens when you increase pressure? For gases, of course, well, greater number of particles per unit volume, increased frequency of collision, therefore increased frequency of successful collisions. Boom, done, okay? So for those two, it's exactly the same. So what about our Maxwell-Boltzmann? Well, in fact, should we do this now? No, let's not do this now. Let's do some more explanations. Since we mentioned surface area, let's do that, okay? So if we increase surface area for a solid, okay, it's going to have to be for a solid as just as pressure is just for gases. So increasing surface area, I would say that increased number of, I would say no. Yeah. Increased number of reactant particles exposed, able to collide with other reactant. Okay, therefore, increased frequency of collisions, therefore, increased frequency of successful collisions. Like so, okay? So it's very similar, but slightly different. So it's this first bit here that's slightly different, isn't it? Okay, that first bit there. So increased number of reactant particles exposed or able to collide with the other reactant. Increased frequency of collisions, therefore increased frequency of successful collisions, all right? Shouldn't you say per unit volume, more reacting particles per unit volume? Thingy 101, same horse, different jockey, all right? It's just basically saying the same thing, but just in slightly different terms. I think in terms of any exam mark schemes, then they'll accept either, okay? They will absolutely accept either, okay? Surface area isn't on CCEA spec. Yeah, pass. Well, I mean, we don't do the CCEA specifically, okay? But certainly, I mean, it's just general chemistry kinetics knowledge, isn't it? Okay. No, there's no exams. You're absolutely right there. But this is a year 12 live, and you know what? You are going to have some exams at some point and you need to finish the year 12 spec. So that's why we are here. Okay, so this is for year 12s. So that's surface area. Let's address the big one, and that is temperature. Okay, so if we increase the temperature, how are we going to explain this, guys? What is your first sentence? I don't want the whole thing, but if somebody said to you, why does increasing temperature increase rate of reaction? What would your first line of your answer be? Just take a second to think about it, okay, if you need to. Good. Yeah, that's exactly where I start as well. So reactant particles gain kinetic energy. Good. Next point. Yeah, we're all on the same page here. That's great. Yeah, moving faster, Jacka. Okay. More successful collision frequency, more successful collisions, have more sufficient energy to react, more particles have sufficient energy. Well, it's twofold this, isn't it? More molecules exceed activation energy. Yeah. More successful collisions. Okay, good. Miss C, absolutely. Okay, so what we get is increased frequency of collisions. Okay, but there's also an increase in the number of particles that have sufficient energy to react. Okay, so it's like a double whammy this. So this is number one, and this is number two. Now, number one is the same as what we've just discussed before. Because they're moving faster, okay, you're going to get more collisions per unit time, so more collisions per second. So just like increasing concentration or increasing pressure, okay, because let's say 1% of collisions are successful, by increasing the frequency of those collisions, you're going to get more successful collisions. It's just, again, it's down to statistics, it's down to probability. You increase the number of times you do something, you increase the number of times you're going to be successful at it naturally, okay? So it's kind of like, I'll go for my analogy in a second, but the double whammy in temperature is not only are they moving faster, so you get a greater frequency of collisions, but because, as all of you have rightly said, it looks like a greater proportion of them have sufficient energy to react, a greater number of particles that have sufficient energy to react. So not only, let's say it was 1%, so 1 out of 100, let's say more frequent collisions. Well, that's 500 collisions per second, so you're going to get 5 successful ones. So that's an increase. But then the percentage of successful collisions by increasing the temperature, because a greater proportion of those molecules now have sufficient energy to react. So we've increased to 1%. Maybe it's now 5%. Okay, so maybe 25 out of a 500 react successfully. So not only have you got an increase in the number of collisions or frequency of collisions, you are also increasing the proportion of those particles that have that sufficient energy. So instead of just remaining at 1%, it's now at 5%. Okay, so it's a double whammy. Okay, yes, absolutely. Boltzmann curve. Okay, so let's have a look at Boltzmann curve, shall we? Oh, no, we can't do that before we've talked about catalysts. Okay, so catalysts, of course, increase rate of reaction. So if we add a catalyst, what that does is, I think we all know, it lowers the activation energy for the reaction. Therefore, a greater proportion of particles now have sufficient energy to react, and then therefore increase, well, actually it's that, isn't it? Increase in the number of particles, number of successful collisions. That's what I was going to say. Okay. Absolutely, Ibrahim. Yeah, they never get used up. Okay, so catalysts are really, really important. So they remain chemically unchanged during the reaction. Okay, they're kind of like just lowering the bar. You know, they're like those guys when the boxer enters the ring, they kind of lower the ropes for them to get in, if indeed they have that. I don't know, but essentially that's it. Okay, so you only mention activation energy when talking about catalysts. Yeah. Okay, I would only say mention activation energy when you're talking about catalysts. Okay, so let's move on because we got a bit to talk about, haven't we? Maxwell-Boltzmann. So let's do a massive one here and talk about how it actually works. So I'm going to go like this. Maybe that's a bit big, like so. So this here is number of particles. And this here is energy. So what I'm going to do is I'm going to draw a big fat purple line here. And this represents the activation energy. Okay. So this is a classic Maxwell-Boltzmann curve. So this is my analogy. Okay. And run with me on this. So this is a distribution curve. It's a standard distribution curve whereby obviously, that should be at 0, shouldn't it really? But okay, very, very few particles have a small amount of energy, 0 energy, in fact. This never touches the top, the x-axis. The reason this never touches the x-axis is that we cannot be sure there aren't some particles out there with an infinite amount of energy. Okay, so it should never, ever touch the x-axis on the other side, all right? Because like I said, we don't know what the maximum amount of energy a particle can have. It could be infinite. Yes, absolutely. So the area equals the total number of the particles or molecules, okay? So the area under the curve here, that represents the total number of particles that we have, all right? The total number of particles that we have. What does this point represent? Any takers? The mean, Miss C says. Average, most common, modal, most probable. I would say it's the mode. Okay, so this is the most common amount of energy that a particle should have. Ibrahim, Rich, the graph technically shouldn't start like an S curving at the beginning is wrong. Yeah. Oops, that's not right either. You'll see them with a curve on all the time, but there we go. It's neither in or there. You're not going to get picked up on that in the exam at all. So this is the modal amount of energy that that particles will have, is the most common. Okay, so let's say if this was a grade distribution for students doing a test. Okay, let's say I had 100 students doing an exam. This would be the most common grade that a student got. Let's call that a C grade. Okay, just for argument's sake. Okay, now the average is probably somewhere here. Okay, so the average is just to the right of that. I'm literally just picking a point, but it's always just to the right of that mode. That's the average, of course. So that's what we've got. So we've got the mode and we got the average. Okay, so let's get rid of these. Whoops, like so. Now, let's talk about increasing concentration. So this is the area here. These are the particles that have sufficient energy to react, okay? Let's imagine, in my analogy, that the E-act is an A grade, okay? So we want more students to get an A grade. We want more particles to have sufficient energy to react. So how do I, as a teacher, increase the number of pupils, or how could I increase the number of pupils that I have to get an A grade? How could I increase the number of particles that have sufficient energy to react? Well, I could increase the concentration, right? So how does this graph look with an increase in concentration, ladies and gentlemen? Nope, not for concentration. Nope, not for concentration. It doesn't shift to the right at all. larger area, absolutely, okay? It's just exactly the same, but higher. So what we'll have is something like that. So it runs pretty much parallel to the line that we've already got. Because what I'm doing here is increasing the number of molecules. Okay, if I increase the concentration per unit area, so I'm increasing the number of molecules. Let's say I'm making it more concentrated. So I have, let's say, instead of having 100 students I put in for the exam, I'm just going to put in 200 students into the exam, and therefore I'm going to get more A grades because let's say I've doubled the number of students I put in for the exam. Of course, on average, I should get twice the number of A grades. Okay, so it's exactly the same pattern, if you like. It's just that we just put more in there. It's the law of averages. Okay, so that's how concentration affects the Maxwell-Boltzmann curve. So a higher concentration, it goes higher. A lower concentration, it goes lower, like so. Okay, so again, if this was, by using a lower concentration, you've got fewer molecules that have sufficient energy to react. So it literally just moves up and down. So like I said, as a teacher, how do I increase the number of A grades? Well, I'll just double the number of students that go into the exam, so I get more A grades out of it. Okay, so that's concentration. Let me get rid of that. Boom. Now, pressure, they won't ask you, they won't give you a Maxwell-Boltzmann on pressure. Okay, flat, no, we're not even going to talk about it. However, they will in terms of temperature. So that is the one that shifts down and to the right. So what we're going to get is something like that. We're flattening the curve. Okay, so we can see that our mode is now here. Our average is also shifted across, our mean, okay? But more importantly, look at this. This is a massive increase in the number of particles that now have sufficient energy to react, okay? So what we've got is this shifting curve. Now the curve area, okay, the area under the curve, very importantly, is what? What happens to the area under the curve, guys? And this is really, really important. Good, guys. Yeah, it's exactly the same. Because increase in temperature, you're not changing the number of particles you have. You're not changing the concentration, are you? You're not actually physically changing the number of particles you have. So what we've got here is the same number of particles, but the amount of energy they have has shifted. So it shifts down and to the right. So you can see here the peak and the peak. Okay, so it shifted down and to the right. So in my rubbish analogy, this is the case of, right, well, how do I get more students to get A grades? Well, let's revise. Let's flog them. Let's get the whip out and actually, let's force them to revise loads and loads and loads before the exam. And I get more A grades out of it. So the number of students stays the same, but I've just got them to work harder. I've given them more energy, shall we say, by giving them more work and helping them revise a bit more. Okay. So that's what happens when you increase temperature, and temperature has a massive increase on the rate of reaction. As we mentioned before, it not only increases the frequency of collisions, but it increases the proportion of those collisions that are successful because they've got more energy. Okay. No, we don't want to be whipping students. It's an analogy. I don't want anybody reporting me. Okay. So yes, in theory, okay, if I was to crack the theoretical whip at the beginning of the lesson, then yes, okay. In that respect, yes. Physically, no. Right. Last one. What's the last one we can do here? Because again, surface area, we can't show this on a Maxwell-Boltzmann, okay? But concentration, temperature, and catalyst. Good. Catalyst is the one I was thinking of. So what we've got here, of course, is nothing changes as far as the particle is concerned. You got the same concentration, you got the same temperature. What you're doing, absolutely, Raseb, is moving that activation energy to the left. So that will be EACT with catalyst, okay? So that's what we've got there. And of course, what we're doing here is shifting that equilibrium shifting the equilibrium. Oh, so yesterday. Shifting that line to the left, so a greater proportion. Molecules that didn't have sufficient activation energy before, all of a sudden now do. They can get involved in a reaction, okay? Mimi, why is the activation on the right-hand side of the x-axis and not the left? It just happens to be there. I mean, it could be anywhere. It's different for different reactions. Each reaction has its own specific activation energy. So this is just, you usually find it to the right-hand side. Very rarely will it be here or something like that, okay? So in terms of my analogy then, what am I doing? So remember the teacher-student analogy? So I want students to get more A grades. What am I actually doing here to increase the number of A grades that my students get? Just to make sure you guys understand this. If you can get on board with the analogy, then you're laughing. Yeah, exactly. That is exactly what I'm doing, is lowering the grade boundary. So instead of saying, right, 80% for an A, I'm now saying 65% for an A, okay? So yeah, maybe giving you answers, Ruhab, yeah, that's it, okay? But this is what I do all day anyway, isn't it? So yeah, lower the grade boundary. Good. So if you can, you're on board with the analogy with me, you understand what's going on here, okay? Will I ask you to draw for this type of topic? Yeah, absolutely. They will ask you to do that. Either they ask you to sketch a Maxwell-Boltzmann, or they ask you to draw another line on an existing Maxwell-Boltzmann. So show how it will look different with a decrease in temperature, or an increase in temperature, or a decrease in concentration, or an increase in concentration. You need to be prepared to do that. It's not worth that many marks. Usually the explanation comes with it. And again, what you might find is that they ask you to say, okay, so I've increased temperature for this reaction. Use a Maxwell-Boltzmann, or maybe they'll just leave a space there, okay, for you to use a Maxwell-Boltzmann as part of your explanation. Okay, and what you find is that using these Maxwell-Boltzmanns, it helps you explain the collision theory much more easily. So if I had this and my explanation was to, if my question was to explain why adding a catalyst increases the rate of reaction, you could say, oh, normally without a catalyst, this area here represents the number of particles that had sufficient activation energy and therefore had a successful collision. With the addition of a catalyst, you now increased the proportion of molecules that have sufficient energy. You can see it clearly in your Maxwell-Boltzmann. So my advice to you is, you could probably do this on one page, okay? Split your page into 4, okay? Have temperature, concentration, catalysts, and then you've got surface area and pressure and another. And so I'll tell you what, if I can show you like this, just split your page into 4. You've got temp, conc, catalyst, and then you've got surface area and pressure. Okay, so here you could have your explanation and your Maxwell-Boltzmann, your explanation and your Maxwell-Boltzmann, explanation and Maxwell-Boltzmann. Here, you've just got your 2 explanations because you don't need a Maxwell-Boltzmann for that. So summarizing these on one page is really, really handy. And these are like stock answers, don't forget, guys, okay? Chances are you're going to be answering the question in an AS paper on this, all right? So be prepared and, have that. You can make yourself a cheat sheet if you like, okay? Our teacher literally made us do this for all the different conditions. Yeah, why not? I think it's important. There's a lot of room for stock answers in chemistry, and this is one of them. Like we talked about for ionization energies and so on and so forth. Okay. Wow, Jackie didn't even touch on this topic in class. Well, you definitely need to do it. What exam board are you, Jackie? Yes, I have summarized it for you anyway. Yes, in the in this, and obviously in the content guide as well. That's summarized for you. Okay. So you do need to do this. It's really important. OCR. Yeah, you definitely need to know this for OCR. Yeah, and that does sound like an old question, Ibrahim, a very old question. In fact, some of those older spec questions, I think what I'm going to do over the summer is try and lift out the good, big old spec questions, which ask you to just lay out what you know from start to finish. Okay, they are really, really good. Okay. Oh, you didn't get to it, Kerry. Okay, well, we got you covered now, right? We got you absolutely covered. Okay. EdXL, yeah, absolutely. You all need to know it. Okay. Kinetics is a standard thing in all A-level specifications. 100%. It's in all of them. Okay. Really, really important one. Okay. So, I mean, in terms of the theory behind it, that's all you need to know. Okay. That's all right, Kerry. No problem at all. So in terms of the theory of it, that's all you need to know. Literally, that's all we need to know. So yeah, Mimi, absolutely. Sorry, I did see your previous question. Yeah, most of the time, particles do not have enough energy to react a lot of the time. Okay. So to access the content guide on the TT website, basically through the exambulance, the top section in the exambulance, you can click on one of the 3 buttons at the top for your exam board, and it'll take you through to the content guide where I have unlocked certain aspects, certain content for you. Okay. So yeah, there's not a lot in there that I've unlocked because it wouldn't be fair to our subscribers if we were giving everybody free access. But we're changing that up next week. We'll talk about that towards the end of the week. Okay. Yeah, it is going to be. So starting from next week, we're just going to be on Zoom. We're not going to be live on YouTube. So, you'll access it via the free Exambulance course. So it's still going to be free to access for everybody. It's just not going to live on YouTube. You're just going to have to be in the Zoom room. Okay. So yeah, that's what we're going to do. We're going to be mixing that up a little bit next week. Okay. And we are still going to be checking in with you daily, 100%. Okay. No. We're just having a slight change of tact, but equally, we're still here for you every day. Okay, we're still here for you every day. Yeah, we're gonna put out a new schedule and stuff like that. Yeah. Zoom uses a lot. Okay. So the classes won't be saved, but then like I said, we're doing something different for you. Just watch this space, don't panic. Anyway, so I want you to imagine this actually. Mimi said that actually most of the reactants don't actually react, but then we know that reactions go to completion. All right, we know that we run out of a reactant. So if most of the reactants don't actually have sufficient energy to react, what actually happens to them? Well, let me show you. As the reactants get used up, this is a standard distribution curve. As these react over here, the concentration of the reactants goes down, right? We're all agreed with that. As they get used up, their concentration decreases. So this curve then will shift like so. And then these will get used up. And then the concentration will go down again and it'll shift like so. And these will get used up and then that'll shift and then these will get used up. So you can see how the concentration goes down. The number of the proportion of reactants stays the same. Okay, but obviously fewer of them, and of course the rate slows down as they get used up. So eventually you end up with this. Okay, really like low, kind of hardly a curve at all. Okay, I'm glad that makes sense. Absolutely. Okay, so they can gain enough energy. So it's just they have this standard distribution. There's a certain amount of energy to go around and it's distributed in this way. And as they get used up, the energy gets redistributed and the others actually get enough energy to react eventually. Okay. Yeah, they can gain energy through collisions. You're absolutely right. Okay, so that's how a reaction can go to completion. As the concentration of reactants goes down, it gets redistributed, and it's always these in this section over here that actually get reactions. Okay, and hence reactions go to completion. Absolutely, Ibrahim. Thank you very much. Okay, so let's talk for the last kind of 10 minutes about practicals. Okay, so there are a number of different practicals that you can do. Okay, so remind me, ladies and gentlemen, or remind each other, which practicals have you done? Which kinetics practicals have you actually done? Jacket, none, just none at all. Okay. Wow. Really? That's crazy. Aussie, thiosulfate, I think you're talking about there. Yeah, disappearing cross. Okay, good. So some of you, most of you haven't done any. That really surprises me and worries me, in fact, because, you know, you have to do these practicals. Okay, so thiosulfate one. And HCl. Okay, so thiosulfate and HCl one, that is where you have some sodium thiosulfate in here, S2O32 minus, okay? And underneath this conical flask, you have a black cross, all right? Now what we do is we add hydrochloric acid to it, and there's a reaction. And the reaction produces solid sulfur, which is a yellow solid, okay? And it goes cloudy. So what you'll find is that, I'm going to use this, okay? It goes cloudy over time. And what you're doing is you're looking down through that conical flask, through the solution at the black cross. It is a precipitation reaction. So of course, when the black cross disappears, when you can no longer see the black cross, i.e., so much sulfur has been produced, so much precipitate has been produced, it obscures your vision. That's when you stop the timer, okay? Okay, Megan, it is a specified one for AQA, I think, this one. But yes, most of you will have probably done it at GCSE, okay? So what we can do here is we can do a number of things. We can do this practical by changing the concentration of HCl. We can also change the temperature. Okay, so we can do this over a range of temperatures. Now it's known as the initial, okay, rate of reaction. Initial rate practical. Okay, so what we're doing here is looking at just one reaction at a time. So a number of different runs. So what we, yeah, absolutely. You can use water baths with this, Hadia. Yeah. Okay. So if you were changing the temperature, maybe you do it at 20 degrees C, 30 degrees C, 40, 50, 60, and 70 or something like that. So you're doing a number of different practicals. All of these, you get a time. Okay. So you're timing how long it takes for the cross to disappear at different temperatures or different concentrations. So exactly how the rate of reaction changes with temperature, we keep everything else the same, the concentrations and the volumes, okay? Really, really important. So we've got a bunch of time. So at 20 degrees, I don't know, it took 62 seconds. This one here was 50, 42, 35, 28, and 19 or something like that. So you can see there's a decrease in time as the temperature increases, okay? What's oh no? Uh-oh. Damn it. Oh, I'm back again if you refresh the page. Yeah, refresh the page. We're back. We're back. We're back. We're back. What is going on with YouTube at the moment? Okay. So we get a decrease in time as we increase the temperature. Okay. We get a decrease in time as we increase the temperature. So how do we turn time into rate? Because it is about rate of reaction. It is about rate of reaction. How do we turn this time in seconds into a rate? Oh, close, had you? Very close. That's it. 1 over time. Good. Okay, so we do 1 over t, and that gives us our rate. So our rate is just per second. Okay, so we've only got a time. Okay, we've only got a time. And there's a few different practicals whereby, you know, this is the case. All right. So you do like the, what's it called? The iodine clock. That's another one. Okay. So 1 over time gives you your rate, and then you plot a graph and you can see exactly what it is or how it is that temperature affects rate. Okay. We can change the concentration of sodium thiosulfate. We tend not to. It's more reliable to change the concentration of HCl. Okay, so that's what we tend to do in this practical. Okay, iodine clock. Yeah, iodine clock's a difficult one. We're definitely not going to have time to go over that today. Other ones are maybe an acid and a metal. Okay, so here you'd have your conical flask, you'd have a bung with a delivery tube like so, and your plunger. Okay, and this is a gas syringe. So as this happens, obviously we're going to get ZnCl2 and hydrogen gas. Okay, the hydrogen gas forces the plunger backwards. Scientific diagrams, there's not many you need to do, but yeah, okay, right now, but yeah. Oh, hang on. So then you use the arena equation 1 over t and the x-axis run rate. Yeah, Ibrahim. Yeah, the year 13 stuff. Year 13 stuff. Do you need to know the balanced equation? I'm pretty sure anyone they give you, they'll give you the equation in the exam, unless it's a specified prac, a specific specified prac, if that makes sense. In which then I would definitely need to know it. Okay. So this is 0, and what we're doing is we're measuring the volume of gas, okay, as it's produced over time. So we plop the zinc in there, we start the timer, and then at time intervals, so maybe every 10 seconds, for example, you'd record the volume. Okay, so at 10 seconds, it might be here. At 20 seconds, it's here. 30 seconds, it's here. 40 seconds, it's there. So, of course, you're going to get an increase in the volume of hydrogen produced over time. Okay, you can do this as long as there's a gas produced in a reaction, you can use this method. So what we're going to get here, this is not initial rate practical, it is actually continuous rate practical. It's known as continuous rate prac because you do one prac and that's it. Okay, and you're continually taking recordings over time. And what you'll see is, let me get rid of this. What you'll see is this sort of thing. Okay, so other thiosulfate and HCl1, the same practical or different? So these are two different practicals that I'm talking about right now. Okay, two different practicals. So you're going to get this sort of recording. Okay, so this will be time and this will be volume of H2, okay, in centimeters cubed. So when we've got a graph like this, okay, we can actually work out a rate. So how would you actually work the rate out for this type of practical, the initial rate? How would you find the initial rate of reaction here? Boom. Yeah, absolutely. You find the tangent. So your initial rate would be here. And of course, what you need to do is dy by dx equals the gradient, which of course equals your rate. And your rate will be in centimeters cubed per second because the volume of H2 is in centimeters cubed and your time is in seconds. Okay, so those are the two major types of pracs. There are other practicals that you could do, okay, but they're going to come under one of these two different types. Either it's an initial rate practical, like this one, whereby you do a series of experiments, okay, and you're just waiting for the reaction to stop or go to completion or get to a certain point, okay? You're not measuring anything over time, you're just timing it. It finishes when it finishes and you stop your timer. Whereas on the other side of things, you get your continuous rate prac, whereby that actually just goes on and on and on. You're taking continuous readings over time, okay? So that's it. So when over t is a variable on the x or the y axis. So when you do rate, what I would say is once you've done this, okay, your 1 over t, let me just go over the page. So your rate would be here, 1 over t, and let's say you're changing concentration of HCl, okay, you'll have a graph like so, okay? So that's what you're going to get. Yeah, we're definitely going to do some exam practice. Absolutely, Jacka. Yeah. Does this graph flatten over time? No, because, I mean, there's no time on there for a kickoff, but as long as you keep increasing the concentration of HCl, you should increase the rate, okay? But the first one, yes, this one, yes, it will do, okay, because it will go to completion. It'll get to the point where either all the zinc or all the HCl is used up, and it will slow down and reach where it plateaus. That's where the reaction is completed, and it will flatten, okay? So we're going to have to stop there, guys. God, time flies, doesn't it? Really, really does. So we're going to do, I can't remember what we're doing tomorrow. Lost my train of thought. Anyway, no Alexa today. I've turned Alexa off. She's not listening. Oh, cool. We're doing some mole calcs tomorrow. Excellent. Well, I'll tell you what, I'll give you my foolproof method for mole calcs tomorrow. How does that sound? Okay. And obviously we'll do some classic questions as well. We'll do some classic questions. So again, thank you very much for coming, guys. Don't worry, there is going to be a slight change next week, as Rich probably mentioned to you in the biology. But you know what? It doesn't matter. We've got you covered. Slight change, but there we go. I do have a black belt in mole calcs. You're absolutely right there. You're absolutely right. I wrote that. Cool. So thanks again, guys. I will see you guys tomorrow at 2 o'clock.